Hey everyone, welcome. Today we're tackling a Leetcode problem called total characters in string after transformations 1. It sounds a bit complex, but don't worry, we'll break it down step by step and find an efficient way to solve it. Ready? Let's dive in. Okay, so what's the goal? We're given a starting string, let's call it, and a number, which tells us how many times we need to transform the string. The transformation rule is interesting. We look at every character in the string. If a character is, we replace it with the two-character string. If it's any other character, like up to, we just replace it with the next letter in the alphabet. So becomes, and becomes. We have to perform this transformation exactly times. After all those transformations, the string might get really long. But we don't need the final string itself, we just need its length. And because the length can become huge, we need to return the answer modulo 10 to the power of 9 plus 7. Let's walk through the example they gave us. The starting string is, and we need to do two transformations, so we draw as two. First transformation. Becomes. The first becomes, and the second also becomes. So after one step, our string is, its length is 5. Now for the second transformation. We take becomes. Now the first, remember the rule. It becomes and the second also becomes, so the final string is, what's the length of, let's count. 1, 2, 3, 4, 5, 6, 7. The length is 7. So the answer for this example is 7. Notice how the character made the string grow longer in the second step. Okay, what's the most obvious way to approach this? We could just do what the problem says, right? Start with the string, apply the rules to get the string after one transformation, then transform that string, and keep going times. Finally, we just return the length of the final string. But let's think about that rule. Becomes, that means one character becomes 2. What happens if we transform becomes giving still length 2? What about it becomes then? See, the length can increase, and it seems like it could grow quite fast, maybe even exponentially, especially if we generate lots of. If the number of transformations is really big, like a billion, we definitely can't simulate the whole string. It would become astronomically large. We need a smarter approach that avoids building the actual string. We only need the length. Since we only care about the length, let's track how the length generated by a single starting character changes over time. Let's define, say, L of char, k, as the length of the string you'd get if you started with just and transformed it exactly times. What's the length after steps if we started with, say, well, after one step, becomes twice 6 x, so the length after step starting from n2 should be the same as the length after k minus 1 steps starting from n2. This works for any character except what about? If we start with after one step it becomes twice 6 step, it becomes twice 6 x, so the total length you get after k minus 1 steps starting from n2, plus the length you get after k minus 1 steps starting from a. Our base case is simple. After 0 steps any single character. We can turn this idea into a dynamic programming approach. Let's use numbers 0 through 25 to represent through, let dp of k, I be the length after transformations, starting from the character represented by index. So, for any character through indices 0 through 24, the length dp of k, I is just equal to the length from the next character after k minus 1 steps. That's dp of k minus 1, I plus 1. For index 25, the length dp of k, 25 is the sum of the length from index 0 and the length from index 1 after k minus 1 steps. So dp of k minus 1, 0 plus dp of k minus 1, 1. And we should remember to take the result modulo, our big number. The base case is dp of 0, I bas equals 1 for all characters. To get the final answer for the original string, we just sum up the lengths dp of t, index of c for every character in the original string, again taking the modulo at the end. This dp idea seems promising. We're only tracking lengths, not the whole string. But there's still a catch. Look at how we calculate the values for step. We need the values from step k minus 1. This means we have to compute the lengths for step 1, then step 2, then step 3, all the way up to step. How large can be? The problem constraints often allow to be huge, maybe up to a billion, or even more. If there's a billion, doing a billion steps, even if each step is fast, just 26 calculations, is still way too slow. We'd need something faster than calculating step by step. Okay, so the step-by-step dp is too slow if is large. But notice something important. The way we calculate the lengths for step depends linearly on the lengths from step k-1. Each new length is just a sum of some old lengths. Whenever you have this kind of linear relationship between states, you can often use matrices. Let's imagine a list, or vector, containing the 26 lengths for step. The length starting from all the way to, let's call this vector v of k. It turns out there's a fixed 26 by 26 matrix, let's call it, that transforms the vector from step k-1 into the vector for step. That is, v of k equals multiplied by v of k-1. If this is true, then v of 1 is m times v of 0, v of 2 is m times v of 1, which is m times v of 0, or m squared times v of 0. Following this pattern, the vector of lengths after steps, v of t, must be raised to the power of multiplied by the initial vector, v of 0. And the cool part, we can calculate m to the power of t much faster than doing multiplications, using a technique called binary exponentiation, or matrix power. Let's figure out what this magic matrix looks like. Remember our DP rules. The length starting from at step comes only from the length starting at step k-1. So in the matrix, the first row, representing should have a Karkic second column, representing zeros everywhere else. The length starting from at step comes only from at step k-1, so the second row has a in the third column, and zeros elsewhere. This pattern continues. The row for character gets its value from column I plus 1. This goes all the way up to the row for index 24, gets its value from the column for index 25. Finally, the row for index 25. Its length at step comes from both amvers krenele NumPy minus 1. So the last row of NumPy has a vector row frey in the first column, and a vector row frey in the second column, and zeros everywhere else. That's our 26 by 26 transformation matrix. So here's the plan using matrices. First, set up our modulus value, that big prime number 10 to the 9 plus 7. Second, create that 26 by 26 transformation matrix we just figured out. Third, calculate raised to the power of using binary exponentiation for matrices. Let's call the result m power t. Remember to apply the modulus during the matrix multiplications. Fourth, we need the final length vector, v of t. We know it's m power t times the initial vector, v of 0. What's v of 0? It represents the lengths after 0 steps, so every character just has length 1. It's a vector of all ones. Multiplying m power t by a vector of all ones means the result, v of t at index, is just the sum of all elements in the ith row of the matrix m power t. Fifth, we initialize our total length to 0. Sixth, we loop through each character in our original input string. For each character, find its corresponding index, like 0 for 1 for etc. Seventh, find the sum of the row in m power t corresponding to that index. This sum is the length that this starting character contributes after steps. Eighth, add this row sum to our running total length, making sure to take the modulo. Finally, after checking all characters in the original string, return the total length. Alright, here's the Python code implementing the matrix exponentiation approach. First, we define our modulus. We have a helper function that takes two matrices and returns their product, making sure to apply the modulus to each element of the result. We use NumPy here for potentially faster matrix multiplication, but we need to be careful with large numbers and modulo, so we use object dtype and loop for the final modulo application. Then, we have matrix power. It takes a matrix and an exponent, which is our papado. It calculates to the power of using that efficient binary exponentiation method. It starts with the identity matrix and repeatedly squares the base matrix, multiplying the result in when the corresponding bit in is set. Again, all calculations use our matrix mult function to keep things under the modulus. In the main method, if is 0, the length is just the original length, so we handle that edge case. Otherwise, we construct our 26 by 26 matrix exactly as we discussed. We then call matrix power to get raised to the power of storing it in m power t. Next, we calculate the sum of each row in m power t. Remember, the sum of row gives us the final length if we started with the single character corresponding to index. We store these sums in a list called row sums. Finally, we iterate through the original input string. For each character we find its index, 0, 4, etc. Look up the corresponding row sum from our row sums list, and add it to our total length, taking the modulo at each addition. After summing up the contributions from all starting characters, we return the final total length. Let's look closer at the matrix multiplication function. It takes two matrices, and both assumed to be 26 by 26. It calculates their product. We use NumPy's .product function here, which is generally efficient for matrix math. We create a result matrix initialized to zeros. Because the numbers can get large before we take the modulo, we use to avoid potential overflow issues with standard integer types. After NumPy calculates the dot product into C_NP, we need to apply the modulus to every single element in the resulting matrix. So, we loop through each row and column, and set the element C of R, C to be the calculated value modulo. Finally, we return the resulting matrix. Now for the matrix power function. This calculates to the power of efficiently. It starts by creating an identity matrix. The identity matrix is like the number for matrix multiplication. Multiplying by it doesn't change anything. We'll build our final result in ResList. We also have our matrix, which starts as the core idea is to use the binary representation of loop while is greater than 0. Inside the loop, we check if I is odd. If it is, it means the current power of represented by is needed in the final result, so we multiply our current result ResList by storing. We use our matrix mult function for this. Whether was odd or even, we always prepare for the next iteration by squaring the matrix, that is, equals times. This corresponds to moving to the next higher power of 2. Finally, we divide by 2 using integer division. This effectively shifts the bits to the right, letting us look at the next bit in the next iteration. Once becomes 0, ResList holds the final result of raised to the power of the original all done modulo. And here's the main part again, putting it all together. We handle the simple case where is 0. Then, we build the transformation matrix as a list of lists called mList. We fill in the ones based on the rules. M of I, I plus 1 is 1 for through, and M of 25, 0 and M of 25, 1 are 1 for. We call our matrix power function with mList, and to get the matrix M power T. Next, we compute the sum of each row in M power T. We use a list comprehension for this. For each row in M power T, we calculate its sum, and take the result modulo. This gives us the list row sums, where row sums at index I holds the final length contribution from starting character. Finally, we initialize total length to 0. We loop through the input string. For each character we find its alphabet index char idx, using the function to get character codes. We look up the value in row sums at that index, and add it to total length, remembering the modulo. After processing all characters, we return the total length. So how efficient is this matrix approach? Let's analyze it. Building the initial matrix takes constant time, basically 26 squared operations. Multiplying two 26 by 26 matrices takes roughly 26 cubed operations, which is also a constant, although a larger one. The matrix power calculation involves about 420 pi coms matrix multiplications, whereas the number of transformations. So this part takes around 26 cubed times log time. This is the most significant part if is very large. Calculating the row sums takes about 26 squared time. Finally, summing the results for the initial string takes time proportional to the length of, let's call it. So the total time complexity is roughly, big O of n plus 26 cubed times log t. Since 26 cubed is a constant, we can think of this as order n plus log t time complexity. This is much faster than the original order n times t simulation, or the order 26 times t targ p approach, when is huge. What about memory? We need to store a few 26 by 26 matrices. The amount of memory used is constant, specifically at 26 squared, regardless of the size of OR. That's very space efficient. Alright, let's quickly recap the journey. We saw that simply simulating the string transformations step by step wouldn't work, because the string could get incredibly long, especially with that becoming rule. The key insight was to stop thinking about the string itself and focus only on the length. This led us to a dynamic programming idea, where we tracked the length generated by each possible starting character through after steps. However, even the DP was too slow, because the number of steps could be enormous. The breakthrough came from realizing the DP calculation was a linear recurrence. This allowed us to use the powerful technique of matrix exponentiation. We built a transformation matrix that updates the length vector from one step to the next. By calculating raised to the power of using the fast matrix power algorithm, which takes logarithmic time with respect to, we could find the length contribution of each possible starting character after steps. Finally, we just needed to sum up these contributions based on the characters present in the original input string to get our final answer. This gave us a solution that's efficient in both time and space. Hope that explanation using matrix exponentiation made sense. It's a really useful technique when you see those linear recurrences and a large number of steps. If this helped you understand the problem better, feel free to hit the like button. Consider subscribing for more Leetcode breakdowns like this one. And if you have any questions or alternative ideas, drop them in the comments below. As always, thanks for watching, keep practicing, and happy coding. I'll see you in the next video.